Okay, so in example 4.3.5, we're given some distributed parameter models and we want to calculate the supply voltage necessary under a couple different line lengths. And so the first one, it's a short line, and the second one, it's a long line. So if the line is below 240 kilometers, we can use one of these approximation models, and the cutoff there is 60 kilometers. So less than 60 kilometers, we call that a short line, and we can use a very simple series impedance model. Less than 240 kilometers, so greater than 60, less than 240, we call that a medium line. That model, there's a couple. I'm introducing one in this class that we call the nominal pi circuit, because it looks like the number pi. Here's your input end here. There's a shunt capacitor that is a value C over 2. Then there's the same model, and there's another shunt capacitor. So this is R, this is L, this is R, this is L, and this is C over 2. So you can see you kind of have this pi shape as the model with the passive components on it. That's where it gets its name. And then of course if it's above 240, that's the long line, which is what we did in example 4.3.4, so I won't go over that again. So we're going to solve this for both the short line condition and the long line, or the medium line condition. We're going to find the input voltage for both of them. So let's do part A first. We've got this model. We've got a series resistor, series inductor. We call this the receiving end voltage. That's the voltage that's going to the load. So we've got the load current, or the receiving end current, and in the input we've got the source current and the source voltage. So you can see from this model that the sending end and receiving end current are equal, just because that's one branch, where VR plus IS times Z is going to be equal to VS. So that's the solution for the short model, is we need to know what that current is. We can replace that with maybe an R, might make more sense, right? There we go. So that's kind of our solution method, is we need to solve that. In these short models, we don't use the distributed parameters, we use lumped elements, so I want that to be an R, and an L, where R is given by the distributed parameter per unit length times the length of the line, and L is equal to L prime ohms or henries per meter or per kilometer times the length of the line. Now in this problem we were given reactances instead of capacitance and inductance, so we'll have to watch how we handle that. That was intentional because there's a little bit of a trick there that I want to show you, particularly for the capacitance in the medium length line. So let's go ahead and calculate our model values first. So R was, the value we were given in this example was 0.00893 ohms per kilometer, and the length of this line was 50 kilometers. Multiply those together, you get 0.4465 ohms. And then we want to know what this value is right here, Jx sub L. So Jx sub L is just going to be equal to J times whatever the L prime value was, or X sub L prime value was. That was 0.5858 ohms per kilometer, again times 50 kilometers. So that gives me the value of J 29.29, right? so I just want to do a little aside real quick. A lot of times we're given L prime, sometimes we're given XL prime. And if I'm given L prime to calculate XL prime, it's just J, well, typically it's 2 pi FL prime. And so L is equal to L prime times L, and we can see that X sub L is just equal to X sub L prime times L. From that seems straightforward, but it becomes problematic later for the capacitance. So it was just a quick aside. I wanted to point that out, that everything I've done so far is correct from a distributed parameter model. So if I want to use this model that I'm showing right here, I need to know receiving end voltage V sub R right here. So it was specified in the problem statement that this was 115 kV line. That's on a line-to-line basis. So I need to divide that 115 kV by root 3 to get on a line-to-neutral basis. And so that's going to give me 66.4 kV. I then need to know what the current in the going into the load is. What is IR? And that in this model is also equal to IS, so you can call it either, but IR is going to be the power divided by the voltage, the apparent power divided by the voltage. This was a 75 megawatt lagging 0.85, so that's 75 megawatts. That's three-phase, so I divide by 3, but that's watts. I need to divide that by 0.85, the power factor, to convert that to VAR, and then I need to know what the power factor angle is. This is lagging, so it's a negative angle. No, it's not. It's a positive angle. And then I need to divide that by the voltage, which was 66.4 kV. Then I want to take the complex conjugate, which is why I got confused about that negative sign. If you do that, you're going to get a current of 442.98 at an angle of negative 31.79 degrees amps. So applying this model, the sending end voltage is just the receiving end voltage plus the current times these distributed parameters. So giving myself a little bit more to work with, a little more white space. The sending end voltage is just going to be the receiving end voltage plus IS times the series impedance. So that's 100 amp, I already did the math, excuse me, 66.4 angle 0 degrees plus 442.98 angle negative 31.79 degrees, and then that series impedance was 0.4465 plus J 29.29. And so my sending end voltage, if I just toss that into my handy dandy calculator, is 74.2 kV at an angle of 8.5 degrees. So that's if the line was 50 kilometers. How does the input voltage change if the line was 150 kilometers? Well, now I need to switch to this line over here. So that's what we'll be solving next. So give myself some more writing room here. So again, let's take a look at this model so we understand what the solution method is. We've got a capacitor that's a shunt, a series impedance, and then a capacitor that's a shunt again. And this is my VS, this is my IS, this is the, sorry, I labeled those wrong. This is receiving end. The load end is called the receiving end on a line model. I receiving, V receiving. The input current is IS, and Vs, and we're trying to solve for that one right there. The model is to put the whole resistance there, the whole inductance there, half the capacitance there, and half the capacitance there. So you can see that again we're going to do an addition problem. We want to know what the voltage is right here, and we can see that the voltage right there is Vs is going to be I times R plus JXL. So that's the voltage drop in this branch due to that current right there, plus VR. So real similar to what we just solved. There's a complicating factor though, is that we've got a current flow right here, and that's the capacitive current at the receiving end, and I is equal to the load current plus the capacitive current at the receiving end. So I have to do that extra step. But that's the general solution method, is I'm going to use that model, solve for those values, and then again just use that equation to solve for the sending end voltage. So we need to calculate our parameters, R, L, C, etc. So in the problem statement, we want to know, we were told what the distributed resistance was. That was 0.00893 ohms per kilometer, and we need to multiply that by the line length. This is a little bit longer for part B. That was 150 kilometers, so we get a little bit more lumped resistance, 1.3395 ohms. This is a R plus J X sub L for this segment right here, so I want to calculate J X sub L next. That's J times X sub L prime times L, and so that's J. I was told that this line had a distributed series inductive reactance of 0.5858 ohms per kilometer. Again, this is a 150 kilometer line. J 87.87 ohms. So R plus J X sub L is 1.3395 plus J 87.87 ohms. So that's my series impedance of this line. Next, what I need to do is calculate what the value of these capacitors are. I want you to really pay attention here because this gets a lot of people. The value for that capacitor was given as this, 0.36 e to the 6 ohms per kilometer. A lot of people have a tendency to just divide that in half between those two, and it doesn't work like that. So what I want you to do is, if you are given a shunt, if you're given a lumped capacitive reactance, do yourself a favor and just back calculate the lumped capacitance. Don't work in ohms, work in farads. It will give you the right answer every time. So you can work out why that is for yourself. For right now, I'm just going to say please just trust me. So remember that the relationship between XC and C is equal to 1 over omega C. So if I want to solve for C, it's just 1 over omega times XC. So C prime, if I've been given X prime, is going to be 1 over omega X sub C prime. So there I can calculate the distributed capacitance. So that's 1 over, this is an AC 60 hertz system, so that's 2 pi f, or 2 pi times 60, which is 377 radians per second. Hopefully you got that memorized by now in this class. And then X sub C was given to us as 0.36 e to the 6 ohms per kilometer. And so if we do that, we end up with a value of 7.36811 nanofarads per kilometer as our distributed capacitance. So now I want to divide that into 2, so C over 2 is just going to be equal to C prime times the line length divided by 2. So that's 7.36811 nanofarads times 150 kilometers. Oops, that's nanofarads per kilometer. And then I want to divide all of that by 2 because of the model. So that's equal to 1.105 microfarads over 2 equals 0.5525 microfarads. So that is the value for the capacitance on either end of the line. Now to do that solution, if I want to know how much current's flowing here, I don't need a capacitance, I need a capacitive reactance. So I actually do want to calculate J x sub C over 2. And I want to caution you, J x sub, so the reactance of C over 2 is not equal to the reactance of C over 2. Do not make that mistake. I see that so frequently. Work it out for yourself why that's not the case, but I promise you they are not. So if I want to find out the capacitive reactance, I guess I should put a minus J on that. So that's minus J 1 over 377 rads per second. So that's omega, and then what is C over 2 was 0.5525 microfarads. So that's going to give me equal to J 4800 or minus J 4800 ohms. Again, we need to know what the known quantities are right here for VR and IR. It's the same system as before, so the calculations we did up here are the same. It's the same load voltage and the same load current. We just changed the length of the line. So the receiving end stuff is the same. So I'll just remind you that the receiving end voltage we calculated in part A was 66.4 kV at an angle of 0 degrees, and the current going to the load we calculated from the power, and we got 442.98 amps, and it was a lagging minus 31.79 degrees. So that is our values. We've done a lot of math, so maybe we should take a minute and summarize. We have that series impedance right there is equal to 1.3395 plus J 87.87. We have a shunt capacitor there and a shunt capacitor there, and the value of both of those is minus J 4800. We know the voltage coming measured at the end of the line was 66.4 angle 0 degrees kV, and this current in that line right there was 442.98 amps at an angle of negative 31.79 degrees. And what we're trying to solve for is this VR, right? So the next step is we want to calculate I here. We do that by solving this formula. So pretty straightforward. We just need to know what that capacitive current draw is, how much current is going through that capacitor. So the capacitor current is just going to be the voltage across the capacitor divided by the capacitive reactance. The voltage across the capacitor is the load voltage in this model, 66.4 kV. And then we need to divide that by the capacitance, which was minus J 4800. So that gives us 13.83 angle 90 degrees amps of current flowing in that capacitor. That means total current is 442.98 angle negative 31.79 plus 13.83 angle 90, and that's going to give us a current through the RL branch of 435.9 at an angle of negative 30.2 degrees amps. So that's that current right there, I. Okay. Now what you can see from the model, hopefully, is that if I know the voltage at, I'll stop using that cursor. If I know the voltage at these nodes, the voltage at those nodes is just these plus that, right? That's a closed loop. So VR is equal to V sending end plus V, the voltage drop across the RL, which is equal to the sending end voltage plus I times R plus J omega L. So we can calculate the, I've been writing these backwards. This is not R, that's S. That's VR. There we go. Now everything's fixed. So the sending end voltage is going to be our receiving end or load end voltage, which was 66.4 kV. And then we need to find the voltage drop across the RL elements on the line. That's the current flow through them for 35.9 at an angle of negative 30.2 degrees. And then I need to multiply by that series impedance, which was 1.3395 plus J 87.87. So we get a VS equal to 92.2 at an angle of 20.8 kV is our input voltage for that one. So we can compare that to what we calculated in part A. We had 74.2 kV for the sending end voltage, the slight leading angle of 8.5 degrees. Here we've gone up to 92.2 because of the voltage drop. So some of that has to do with the increased amount of lumped resistance and inductance because the line's longer, but some of it has to do with this additional current component that's being drawn by the shunt capacitor that we have to take into account for. So that's the answer there, end of this problem.